Okay, we're ready now to check if gravity is conservative or not. And we're going to simply use the definition of whether a force is conservative or not and try to figure out if gravity is conservative or not. Okay, and what we'll do is we'll take a simple example. We'll take an object of mass m, we'll start it at point A, and we'll have it go to point B along a few paths. Okay, first will be along path 1, which is directly from A to B. Then and let's say that the height is h, then we'll have it go from A to C to D, then to B, and this would be the second path, and so this will be path 2, and we'll find the work done for each of the paths and see if the works match or not. If the works are equal, then we can say that gravity is conservative. If it's not equal, then we'll say that it is non-conservative. Alright, so let's go ahead and find the work done along path 1. And once again, we'll use the definition of work, which is Fd cosine theta. The force of gravity is nothing but mg. The displacement is h, and the angle that gravity makes with the displacement is simply 0, and this gives us mgh. Now let's find the work done along path 2, and that happens to be the work done from A to C, work done from C to D, and then work done from D to B. Now if you look at the work done from A to C, you'll see that gravity makes an angle of 90 degrees with the displacement, and so the work will be 0. Let's just write this down. It will be mg times, let the distance traveled be d, times cosine of 90, plus along C to D it will be mg times h times cosine of 0, and then once again from D to B it will be mg times some d times cosine of 90. Now what you realize is the work done along this part and here is 0, which is from A to C and then D to B, and all that we end up getting is that the work done along 2 is simply equal to mgh, which happens to be equal to the work done along path 1. And with this simple poor man's calculation, we can actually say that gravity is conservative. Now let us do one more thing here, and this is a very useful concept. Let us also find the work done by gravity if it, say, went from A straight to D and then to B. So let's say, once again, I'm just going to draw this again, A, B, and D is somewhere out here. So let us say that it went from A to D and then to B. So let us find the work done by gravity along this path and see what we end up getting. Just for a purpose, let's say that the angle here is theta, and the height is h. So what we need to do is, let's put the block up here. Let's say it goes along this path of mass m. So the work done along this third path, let's just call it path 3, is going to be work done along AD plus work done along DB. Now the work done along DB, we understand, is simply equal to 0. So let's focus on the work done along AD. And now in order to find the work done along AD, what we need to find a few things. We need to first find, we know the force, but what we need to do is find the length of AD. If you look at the right angled triangle that is formed, we see that h is the opposite side. So we know that sine of theta is h over, let's call this length L that we're interested in. And so L happens to be h over sine of theta. Alright, so we have all the components, and what we know is that the force is mg, the length is h over sine theta, and the angle that it makes is nothing but cosine of 90 minus theta. Now, we have a simple trig identity. Now, you can just prove it very quickly. If we have theta here, 90 minus theta, and let's say the sides are A, B, and C, what we know is that sine of theta happens to be equal to B over A, and if you look at cosine of 90 minus theta, is also equal to B over C. Oh, I'm sorry. The sine of theta is equal to B over C, and the cosine of 90 minus theta is also equal to B over C. And so we have a simple identity that sine of theta is the same as cosine 90 minus theta, which we'll use here. Now what we know is that this becomes mg over h over sine theta, mg times h over sine theta multiplied by sine theta, and this ends up being equal to mg times h. So this is the work done along path 3, and so we see that that is also equal to mgh. Now this is very useful because what we realize is that the work done by gravity is simply dependent on the height of the object. Okay, the height that the object has traveled, the vertical displacement. It does not depend on anything else. So for instance, for each of these paths, the work done will be the same. So if an object went from here to here, and if say this height is h, the work done would be the same as if it traveled along some random path here, okay, or say if it went up and then came back down. Alright, so something very useful, work done by gravity simply depends on the height h, and also the fact that gravity is a conservative force. Alright, so in the next video we'll verify if friction is a conservative force or not.